Hi, my name is Dan Burns, and I teach physics at Los Gatos High School. And I'd like to tell you how I used an ocean optic spectrometer to solve a mystery resulting from immersing LEDs in liquid nitrogen. So, the mystery I'm trying to solve is what was observed when I immersed a LED into liquid nitrogen. And it turns out to answer this mystery, we needed our ocean optics red tide spectrometer. I've been using them for 14 years in my workshops and classroom. And so here is what started the mystery. Is after a workshop, I had some leftover liquid nitrogen, and I decided to immerse a green LED in the liquid nitrogen to see what would happen. And you can see it changed.
Green to yellow.
And so I'd heard they changed color and was very happy that it was a very noticeable color change. But then I did a little research and found out this shouldn't have happened based on the theory of how LEDs work with changing temperature. And so why did it turn yellow from green? And so LEDs have a band gap energy. That's the energy electrons have to overcome at the p-n junction. And when they do so, they give off a characteristic color or wavelength of light that's associated with the band gap energy. And so the most likely or the peak wavelength produced by an LED is indicated by the band gap energy. Now, if you cool an LED from room temperature to that of liquid nitrogen, it's going to reduce the energy the electrons have before they cross the band gap, just due to their lack of thermal energy. And so they start off with less energy, so it should be harder for them to cross the band gap. So it effectively increases the band gap energy. Kind of like it's harder to jump across a ditch if you do it from a standing start rather than a running start. Well, if the band gap energy should increase, that means when the electrons jump over it, they should give off higher energy photons, which would have a shorter wavelength. And so the LED peak wavelength should be blue shifted to a shorter wavelength, but we know yellow has a longer wavelength than green light. And so the green LED apparently red shifted to yellow when cooled. Now this is just visual observation. There's more going on, and the ocean optics red tide spectrometer allows us to find out more about that. So this is a spectrum produced by the green LED at room temperature, this lower curve, and then in liquid nitrogen. Now the intensities don't really mean much. It just matters how I aimed the fiber optic cable when I was collecting the data. So if you were to scale them to have the same relative intensity, you would see the peak is almost exactly the same. In the data table I'll show later, you'll see it did blue shift by 2 nanometers, but that's not really significant. So the peak wavelength didn't change. Why did it look yellow? Well, you can see that here. All this light produced by the green, by the room temperature green LED is going to be missing when it's in liquid nitrogen. So we're missing a lot of the green photons that gave it that green color to our eye. And it's probably also enhancing the red and orange. If we were to scale this up to be the same, I think you would see that. But the main thing it looks to me like is the green is missing. And so this says how temperature is affecting the population of electrons that are available to jump the band gap. And so by cooling it, we are missing more electrons that would give up energy on the blue side of the peak and more on the red side, even though the peak stayed the same. And so without the spectrometer, that would have been hard to answer. Now, of course, the next question is what happens with other colors? And so this is a color LED strip. This is infrared, red, orange, yellow, green, blue. The orange and the yellow look very similar to the eye, but they noticeably look orange and yellow if you were just seeing this yourself. And so let's immerse it in the liquid nitrogen. And you'll hear it bubbling as it tries to reach thermal equilibrium.
It keeps operating.
But something is going on.
And it's a little hard to see what's going on. Keep bubbling.
So I let it go for a while, and it'll reach thermal equilibrium, or close. And so you can see we have the infrared you can't see. The red became a little reddish orange. Both the orange and the yellow turned green, and the green turned yellow as before, and the blue stayed blue. And then here we are letting them warm back up. You can see frost building on it because it was so cold, but they go back to their original colors. And so what is going on? Well, we now know that looking at the spectra is the key to finding out what's going on. And so the yellow and orange both blue shifted to green. And so the curve on the right is the room temperature one in both sides here. And so this is the yellow one, and this is the orange one. And the peak wavelength is very similar. The yellow one's just a little broader, and so that's what gives it that yellow appearance to the eye. The orange one's a little narrower, missing some of the orange. But in the liquid nitrogen, the peak is almost at the exact same place, and they both are pretty narrow, and they both appear green. And so even though there is a blue shift, and that does explain that they're going to green to explain the entirety of it, you also have to think about what's happening to the population of electrons when they transition. The ones that were lower energy are missing at the liquid nitrogen temperature. What about the other ones? And so red, definitely blue shifted here into kind of the red-orange. And so to the eye, there was a little bit of an orangish red color, not real apparent, but definitely in the spectra, there's a blue shift. And then in the infrared, even though you can't see it, I was using an iPhone with has a filter on it that filters out infrared, so you couldn't see it in the video. Some video cameras will show infrared. But it definitely shifted it, but not to the visible. And so it started here and then shifted here. And the blue stayed blue, and so why was that? Its characteristic didn't really change much. All that I noticed is in the room temperature, that's the lower peak one here, notice the higher peak here, and then there's a secondary peak. They sort of switch in liquid nitrogen. And so again, we're changing the population of electrons available to make the transition across the energy gap. And then this is my data. So the peak wavelength for blue went from 445 to 422. And so that is this to this. And so they just really changed relative intensity. Really, the blue didn't change much. And so notice the green did a blue shift, but just 2 nanometers. But the others show a 20 or almost 30 nanometer wavelength blue shift. And so the theory that the peak wavelength should shift to the blue because the band gap energy is effectively increased because the electrons, because of their lower thermal energy, have a tougher time crossing, seems to be right. But also this involves how things appear to the eye and what the population is that's available to make that transition. So thanks Ocean Optics for helping solve this mystery.